Here we start with finding a theoretical density of an element. An example here is chromium, because chromium has BCC crystal structure, so it looks like the unit set looks like this shape here. If we move to page 26, that the periodic table is given, we can find its atomic weight to be equal to 52. So A is equal to 52 gram per mole. The radius and the value of N with regard to the previous slide formula. The value of A is known from periodic table. The value of course, we need to know the value of radius, atomic radius, to find the value of volume, and Avogadro is fixed. Based on the crystal structure, we will find the value of N. So we go to first page of the book, where characteristics of selected elements are given in a table, and we go down, look at the chromium with the atomic number of 24. You see its crystal structure is BCC, and the atomic radius is 0.125 nanometer. Based on BCC, of course, there are 2 atoms per unit cell, and we know there is this relation is valid for a BCC, resulting the side of unit cell to be this value. If we plug this value in the relation shown in the previous slide, we will have the final result, which is 7.18 gram per centimeter cube, which is very close to the actual result of density for chromium. Now we go to the crystal structure of ceramics. Bear in mind that because ceramics are composed of at least 2 elements and sometimes more, their crystal structure are generally more complex than the crystal structure of metals. This is just a reminder that in crystals, bonding can be ionic and of course covalent in character. The percent of ionic character increases with the differences in electronegativity. So if this part of elements are from this side and the other elements are from here, of course the differences of electronegativity results higher differences results in higher value of ionic character, and the degree of ionic character, of course, may be very large in crystals or small. CaF2 is an example of very large value of ionic character, and silicon carbide is a small example with small value of ionic character. A common group of ceramics are oxides. Oxides and has oxide structure. In these structure, oxygen anions are larger than metals. Cation. Close packed oxygen in a lattice results in FCC crystal structure. Here, cations fit into interstitial sites among oxygen ions. We talked about different crystal structure, but what determines the type of crystal structure? The first thing in ceramic is the relative size of ions, so the size of cation to anion. As you can see, we have different size of cation to anion. Of course, for this one, we have unstable. This is stable, and of course, this is also stable, but this one is like more stable regarding crystal structure. So the relative size of ion result in different crystal structure. This relative size results in or causes or maximize the number of oppositely charged ion in neighborhood. The second factor which is important in determining the crystal structure is the charge neutrality. If you, as an example, consider calcium fluoride, because the charge should stay neutral, and this is also showing in the chemical composition, there should be twice number of fluorine atoms than the number of calcium in each crystal structure. In other words, in calcium fluoride, each calcium ion has 2 plus charge, which is Ca2 plus, and associated with each fluorine ion, which has single negative charge, F minus. So there must be twice as many F minus as Ca2 plus ions. This is also reflected in chemical formula of CaF2. Okay, let's have a look how the radius of cation to the radius of anion affects the crystal structure. If this radius is very small, like this one, then an ion can collide each other, and this results in an unstable composition. If this radius is increasing so that cation touch the edge of an ion and they do not touch each other, we have the start of stability. And based on the size, the relation of the size, you see we can have triangular, tetrahedral, octahedral, and cubic shape of crystal structure. The coordination number, which is the number of anion touched by cation, is of course here is 2. For this one is 3. For the third one, as you can see here, we have the tetrahedral, so 1, 2, 3, 4. This one is 4 surrounding and 1 up, 1 down, so 6. And this one for cube is of course is 8. Examples of tetrahedral, octahedral, and cubic are these atoms, these ceramics that you can see here. Bear in mind that coordination number is increasing with the increase in cation to anion radius, of course. So as I said, if this radius of cation is very small, this one starts to rattle, it is unstable, and because these are actually touching each other, colliding each other, of course this is an unstable compound. If this one increases until it touches all the surfaces, it will be start of stability, and if there is a little bit of gap, this will be more stable. So we can generally say that we have this relation between this type of crystal structure to this type here. Let's compute the minimum cation to anion radius for a octahedral site, similar to what we observed in the in this slide here, octahedral site. Now we want to calculate the value of, or the ratio of our cation to radius of an ion. You know the coordination number is 6, 4 surrounding, 1 top, 1 down. If you look at this cube, the side of the cube is A, which is because these two, or these are touching, actually these two are also touching. This gap was by mistake. So we have this relation, A is equal to R anion. Of course, the addition of 1R anion, 1R here, plus 2R cation is equal to this side, and according to Pythagoras theorem, we can write down this is equal to root of 2A. Using this relation, if you plug in this relation into here, then we end up to a relation that has only R anion and R cation. And if we continue this, we end up to a relation like this one. Just plugged in this relation into here, and then we can find the ratio of R cation over R anion, which is almost equal to 0.414. This is the start of stability for octahedral site. Bond hybridization is another item that results or affect the shape of the crystal. As an example, if you take carbides silicium into consideration, the electronegativity of silice is 1.8 and carbon is 2.5. Of course, then the ionic character, based on the formula that you had in the previous semester, previous session, previous chapter, is 11.5. This means that almost 89% of the bonds are covalent. As you know from the previous chapter, of course, carbon and also silicium, which is in the same group, they prefer sp3 hybridization. So therefore, for SiC, Si atom occupy a tetrahedral site, so they prefer to occupy a tetrahedral site, which has 4 coordination number. Let's predict the crystal structure of Feo, iron oxide. We want to determine or predict what is the crystal structure for iron oxide on the basis of ionic radi. If we look at the very first page of the book, we can find the ionic radius for Fe ion with 2 positive load. We have ionic radius equal to this value 0.007, and for the Fe3 plus we have another ionic radius, and for anion, which is oxygen, this is the radius. Of course, for Feo we have to follow with the radius related to Fe2 plus. If we plug in these values in the to find the radius ratio, we can calculate it to be equal to 0.55, and because it's 0.55, then based on this ratio the coordination number is 6, and because it falls between 0.414 and 0.732, then the crystal structure for iron oxide is like NaCl, it's octahedral. Of course, the concept in NaCl, which has ionic bonds, is the same. Again, we calculated the ratio of cation to anion radius, and you see it's 0.564, which is still in the same range as previous slide. So the octahedral site is preferred by NaCl. For MgO, magnesium oxide, it's the same. We have 2 negative load here for oxide, 2 positive for magnesium, and the radius R can be found from the first page of the book. And if we calculate the ratio of the radius, we say it's equal to 0.514. Therefore, cation prefers octahedral sites. Therefore, so each Mg or Fe2 plus has 6 neighbor oxygen atoms. Some of the ceramic materials that have equal number of cations and anions are called AX compounds. Here A is referring to cation, and X denotes anion. There are different crystal structure for AX compounds. The most common one is what's happening in NaCl, where the coordination number is for both cation and anion is 6, and therefore the radius is something between 0.414 and 0.732 based on the previous slides. The unit cell of this structure is shown here in the top right corner. Another example, another crystal structure example is cesium chloride, in which the coordination number is 8. Therefore, it has cubic crystal structure. Here, the anions, as you can see here in the left hand side picture, they are located at the corner of a cube, and the cube center is a single anion. A single cation, Cs plus, as you can see here. There are other kind of crystal structure type in which that you can find them in page 85 and 86 of your book. And now we go to the next step, which is the calculation of density for ceramics. The calculation of density, to calculate the density of ceramics, we use this relation, which n prime is the number of formula units per unit cell. Sigma A subscript C is sum of atomic weights of all cations in formula unit. Sigma AA is the sum of atomic weights of all anions in formula unit. Vc is the volume of unit cell, and Na is Avogadro's number. As you can see, increase in any one of these two numbers, which is the sum of atomic weight of anion and cation, results in higher density. Now let's compare the densities of different material classes. In this table, as you can see in this table, in general we can say the density of metals are generally bigger than the density of ceramics here, and the second one is bigger than the density of polymers. Why? The general reason, the main reason is that in metals we have close packing or metallic bonding. Also, most of the times we have large atomic masses. In ceramics we have less dense packing and often lighter elements, while in polymers we have low packing density, usually amorphous, and lighter elements like carbon, hydrogen, or oxygen. And for composites, which is here, we have of course intermediate values from glass fiber down to wood. Okay, now we move to another group of ceramic, which is silicate. These materials are made mainly from silicon and oxygen, and these are the materials that are most common found in Earth, silicon and oxygen. Si has 4 free spots for electrons, or to share electrons, and oxygen has 2, so these can make elements like SiO2 or SiO4. If we have SiO4, we will have a tetrahedral crystal shape. For SiO2, which is also known as silica, we have different forms. This is called polymorphic forms. One of the famous forms of SiO2 is quartz. There is strong covalent bond between silicon and oxygen that results in high melting temperature, around 1700 degrees Celsius for this material. Another form of SiO2, which is cristobalite, is shown here in this picture. For various silicate for SiO4, 1, 2, or 3 of these oxygen actually share by other tetrahedra to form another complex shape, as you can see. So for example here, or they can share like this one, or they can share in this form, or they can make a chain, as you can see in figure 413 of page 91. This shape have different formulas, as you can see here. For these ion structures, the presence of cations like Ca2+ or magnesium 2+ or aluminum serve 2 roles. Now the first one is that they compensate the negative charges from SiO4, so that now we have a neutral body. The second reason is that, or the second role is that these cations they bond ionically to SiO4, and they bond these tetrahedra together. Glass structure is also a common form of silicate structure. If this tetrahedron or SiO2 has no impurities called fused silica, similar to quartz that you can see here. They can also be found with some impurities like Na or sodium or calcium, aluminium, and bore, similar to this picture that's shown here. We continue with other structures for silicates, actually layer silicates, in the next section. Thank you.